It's really interesting to understand that up until the end of the 19th century or the beginning of the 20th century, people thought that maybe our galaxy was the only one in the universe. Or in other words, that our galaxy was the universe, even though people had already made amazing drawings of the observations that they were doing of what people called spiral nebulae, and also some of the first photos of Andromeda were also taken, like this one. However, even though we had seen and discovered other galaxies, we actually thought that they weren't other galaxies. And instead, we thought that things like these were actually solar systems information within our own galaxy. Fortunately, because of the work of Henrietta Leavitt, who was born in Lancaster, but on the other side of the pond, we were able to finally start measuring distances to objects much further away than, for example, what parallaxes would allow us to do. And by applying that technique, we were actually able to establish these spiral nebulae as actually being way, way outside our own galaxy. What Henrietta Leavitt discovered was that specific stars, there are variable, Cepheid variables. Their period, or the period of the variation, actually allows you to know or predict what is the peak absolute magnitude in, say, the V-band. Therefore, if you measure the period of this Cepheid variable and you measure some apparent magnitude, because you can predict the absolute magnitude and the relation between absolute and apparent magnitude is just distance, you can actually solve for the distance. We already saw this example in a previous section, but I'm recovering it here to make sure that you really attempted. The details are also in the lecture notes, and the worksheet even had something similar. So I assume that you know how to use Leavitt's law. Essentially, if you measure some period of Cepheid, you can actually get the peak absolute magnitude in the V-band. And if you measure an apparent magnitude in the V-band, you can solve for the distance. But if you do have any questions about how to apply this or where this comes from, please just get in touch. Leavitt's law was really crucial so that we could start measuring distances to things well beyond our Milky Way. But at the same time, people are also doing spectroscopy, and especially because the universe is made of hydrogen, it was relatively easy to measure hydrogen lines and to actually look, for example, at stars within galaxies and what absorption lines were doing, or even the ionized gas and looking at emission lines. What people realize is that most galaxies that were way, way beyond our Milky Way actually had a positive shift in wavelength. And we'll see that we're going to call this Z a redshift. Redshift is just the observed wavelength minus the one you expect at rest frame divided by rest frame. In other words, what people started realizing is that for most spiral nebulae and other nebulae that turned out to be galaxies, they all showed a positive redshift, meaning they were all kind of moving away from us. We've already seen how we can convert a shift in wavelength in terms of a shift in velocity. So this would also imply that these galaxies were moving away from us really, really far. And most importantly, once Leavitt's law was published and used by Edwin Hubble, it was finally possible to start determining both a distance and a redshift for each one of those galaxies. By combining the measurements from Henrietta Leavitt's law that Hubble did for a few galaxies, and also combining the measurements done by another scientists of the redshift or the recession velocity, Hubble in 1929 really contributed to a huge world revolution. What I managed to find, and together with Lemaître, and now this is no longer called just the Hubble law, but it's actually the Hubble-Lemaitre law, to recognize the contributions of both scientists. What they realize is that the further away a galaxy is, then the more redshifted it is, or the faster it is receding away from us. There's, of course, a few exceptions. Some sources that are relatively nearby actually have negative velocities. This includes Andromeda and also M31 that is coming our way. But for most things that are further away, if you can measure a velocity shift or a redshift, in a way, you can even predict how far away it is, even if you can't find a Cepheid variable to establish a distance to that galaxy. Because redshift correlates so well with distance, we can actually add to what we've seen before in section 2, when we introduced a distance ladder, and I told you that it all starts on Earth by measuring the speed of light and then determining 1 AU. Essentially, with this experiment and Kepler's third law, the following step is to start measuring parallax. And also we can step up in distances by using Cepheid variables. And we'll see in the final section that we can even use these white dwarf supernovas as a distance indicator, but ultimately the largest distances can be measured essentially by measuring a redshift. The larger the redshift the galaxy is, then the further away it is. The Hubble-Lemaitre law has really, really important consequences of how we see the universe. It implies that the universe must be expanding. But what does that even mean? Now, it is important to understand that even though we perceive or we measure galaxies moving away from us, they're not really moving within space-time. They're actually fixed. What is happening is that space-time is actually being created between galaxies. In practice, this creation of space-time is only happening where gravity is essentially null or non-existent, and therefore you can only see it if you're really, really far away from an object like a galaxy. It also means that within galaxies and within our own bodies, fortunately, space-time is not being created, at least yet. One of the important questions is, of course, what is causing this expansion of space-time, and even more so, what is causing the accelerated expansion of space-time, things that you'll definitely cover in cosmology modules, and that we're also going to discuss a little bit in the final section of 263. One thing that's really important to understand about the universe, and especially the observable universe, is that no matter where you are in the universe, we always think that we are in the center. And this is just a consequence of the speed of light being finite and essentially taking time to get to us. Now, let's say that this is the real planet Earth. And when we look around, we can actually see, for example, a few galaxies. All these galaxies will appear to be moving away from us because space-time is being created. But space-time is being created also between these galaxies. And therefore, even if you're looking at somewhere else in the universe, the perception of the universe will be exactly the same. They will also think that they are in the center of the universe. The other important consideration to make is that if you look further and further away, you're actually looking back in time. So you can see some of the first galaxies if you look at the furthest distances, no matter what direction you look at. And also, the ultimate limit to the observable universe is actually the cosmic microwave background. This is the reason why when we look at the universe as a whole, we can actually see all this radiation, the CMB, coming from all directions. And it's also curious to think about the fact that every second that passes, we can actually see the universe 1 second later. And therefore, the observable universe grows every second by 1 light second.